Well, good afternoon. This is week number 3 and lecture B. Okay, lecture B. So if you forget our roadmap, best idea is to check our syllabus. So we are going to follow the syllabus. Basically, we are going to spend about 5 lectures on state model and solutions. Then we are going to focus on controllability, observability, and stability. So this together we have 15 lectures. So then realization part, state feedback, output feedback, and I'm going to add some emerging research topics. So today, we're going to continue to talk about linear multivariable control, and just a reminder that due 11th, that is next Tuesday, right? Next Tuesday. So 10th is our Monday, next Monday. So next Monday after the lecture, we're going to have a 5:45 to 6:45. We're going to do a tutorial so that you may have any hard questions before the deadline for the problem set 1. I'm going to work with you, okay, for 1 hour. So prepare your questions, and I already posted the PS2 problem set 2. So let us record what we did last time, and it's discrete time system. Talk about discrete time linearization and its transition matrix. We spend time also on discretization part. All those are recorded. Today we are going to focus on the solution, the who solution. Okay. So when we say who, that means 2 things. One is the response due to initial condition and due to the control, excitation. So that solution, this part is called zero input solution, okay? This one is called zero state solution, okay? So for whatever, you should recognize this, okay? So I'm going to remind you. So reading materials, chapter 3 and chapter 5. And so now we actually focus on, last time a little bit on this one. So this is the who response, okay? You have 2 things to the system. So you have system, you have 2 things. One is initial state, you have initial condition. Another one is the external excitation, U, okay? So how we can get a Y? Giving U and giving this, okay? How you can get that? The answer is here. The answer is here. This one. The answer is here. This is the answer. So 2 sources of inputs. One is input signal, one is initial condition. And phi is called state transition matrix. Okay, it's a matrix. So why the final solution we can write in this way? Why? So don't take it for granted. Okay? You thought this is straightforward, it's not. So one of the ideas is to do, there are 3 ways to arrive to this. Okay, there's 3 ways to arrive to this. One is called superposition way, one is called direct integration way, another one is called verification of formula, okay? So I'm not sure which one you like. I personally will like the first one. But the first one, you don't feel really comfortable. What they should do is to say, express the U in terms of integration of convolution with the delta, okay? So you know that, you heard about that, you have a signal, you convolute with 1t. 1t is a unit step function. So this is 0, this is ut. But anything less than 0 is 0. Greater than 0 is 1. So this is called unit step. Unit step. This one is exactly the same thing as 0 to t, u tau d tau. It's like integration of that one. On the other hand, ut convolute with delta t, it will be ut alone. Okay? Ut alone. Okay? So that is the way we see it. But this one is exactly like writing a u sigma, delta, t minus sigma, and d sigma, and using this one, t0 to infinity is my u sigma. Okay? Ut, I'm sorry, it's here. So we express the u in such a way, and using this delta as a carrier, okay? Then basically I have infinite many of this kind of u delta add together. So then if we have a linear mapping, okay, actually it's a system, linear mapping. We just insert the u with that formula. So basically you put this one into here, so you get this one. So now we have integral. Then we swap the integral versus h. Okay? So by assuming we can swap, we are already assuming we are going to do a superposition. Okay, so basically this inside is x sigma t and d sigma. Okay, it's d sigma. Okay. So if we do the system like this, and how we can get a single impulse, say for example, x0 is 0, then you have a single pulse in here. I told you what says? This is single pulse. So at sigma, okay, at sigma. So only when t is sigma, it is sigma. So this is a magic thing. So if you write this one, this is a delta. If you write this delta of t, so this is called a unit impulse function, right? But if you simply use this one, it's wrong. They cannot live on its own. So this is called generalized function. Generalized function. So it's only like ut is not 0 when t is not 0. Okay. Okay. Sorry. Ut is not 0 when t is ut is 0. Okay, sorry. U delta t is 0 when t is not 0. Okay, when t is not 0. And it's minus infinity, positive infinity, delta t dt is 1. So, okay? Okay. So that's called generalized function. If you write only this one, it's not good. It's not well defined. So only together it's defined. So we have sticky. Sticky means what you can write ft delta t, okay, is what? Well, what you can say? You cannot say anything about it. Okay? Only you can say that, oh yeah, this is f0 delta t. Okay, you can write this way. This is okay. This is okay. Because this is a sticky, it's always there. Sticky. Yeah, you cannot say beyond than this. Because I know that when t is not 0, everything will be 0. So only when this one is, so this is like this. Okay? So then there's another one is called shift. Shift means if you have a delta t minus tau, you have ft, okay, times this one. This one will give you f tau. Is that right? No, it's wrong. You cannot write it. So you have to write delta t minus tau again. So this is sticky. Okay, still this is not wrong. Okay, this is not wrong. So you have to write this one back so to be right. The only thing you can say that only t is equal to tau is not zero, otherwise it's zero. So however, you can say that minus infinity to infinity to f t delta t minus tau and d t. So that will give you what? F tau, right? F tau, which is correct. So then it's like a nitpick. So you have a point. So you have only one pick up when this is tau. So so the rest are gone. You only need this one. What's the operation? Is this one. So I said this is kind of like impulse in here. Okay. When I say impulse, this one. When I say impulse. When I say impulse here, U sigma is like a magnitude, okay? So delta t minus sigma, because otherwise, only when t is sigma, this is meaning non-zero, okay? Otherwise, it's all zero. But this one itself doesn't make a good sense. So this one is always there. So you also see that. So U sigma and delta t sigma integrates minus infinity. So this will be 1. No, this will be U sigma. Okay, will be U sigma. So in a sense, this one, U sigma, delta sigma, if you draw the curve T here, this is sigma. So this will be an impulse. So impulse meaning the duration is 0, and this one is infinity. Infinity. But just imagine you have a duration like this, okay, like epsilon. This is the height, okay. So if it's unitary, then it's 1 over epsilon. So then this one is 1, right? But here is not. It is U sigma divided by epsilon. Then you send epsilon to 0. What you get is something called impulse. So this guy is U sigma delta t minus sigma. So this is the picture. Okay? I hope you see that picture. So basically, I give you the system an impulse, like acupuncture. Okay? You have a needle. Okay? Poke it. So then see how the system responds. Then we add all these things together. Then it's the real response with respect to the U sigma. So that's the idea, okay? That's the idea. So if we go back and we'll see that when t less than sigma, everything will be 0. When t is sigma, then you have B sigma, U sigma here. Otherwise, when t greater than sigma, you are going to have state transition from sigma to t. That will give you xt. So I hope you will be able to see from here. So x sigma t, we have 3 possibilities. Either 0, okay, or bu at that sigma point, and after the sigma. Okay. So then add together, you are going to have xt due to the ut, and remember, we have this x sigma is u to t, state transition. So I put together, I'm going to get this thing, okay? Integration here from t0 to here. So I have this integration. Non-zero initial condition apply again and superposition. So I end up with this equation. So u, b, phi. So then you get this xt. So this looks. So this is the first method called superposition. So the second method, let's directly do integration both sides to see what's going to happen. So that one using superposition idea. But this one using something probably you like it better. So let's multiply both sides with the inverse of the transition matrix. So I left multiply sigma t, phi in here. So then I have I move this term this side, okay? Then I have left multiply, you have phi bu here, okay? Then, but remember we have a second variable here, ddt will be minus phi at. That's we have seen before. So together we understand this one is actually so because of this one, so I can write ddt phi sigma t, so there's a minus in here. So minus a should be this. So then I put together, then I'm going to have this one, okay? This plus. So then I multiply together both sides. I'm going to do integration. So then I'm going to have this one, and it's the initial conditions here. So this is the initial condition. And on this side, I simply integrate. Then, in the end, be careful, and I left multiply again phi t sigma here. So then I end up, this one is I, and this one is phi t0, and then t sigma. So it's a t tau. So I end up with this one. This is also beautiful. So that's why we need to learn state transition matrix, then we know the solution, okay? So that's another way to go for it. The key point probably is this term, okay? And to have this term, there's a property of state transition matrix, okay? Another idea, the third method is to just insert to verify the formula. So I assume I know this is true and put it back to see whether we can get the original system. So then we know this. So we first try when t is t0, then this is xt0, and put t0 here, this is a identity matrix. This is the identity matrix, so it's x0. So t0 integration, this must be 0, okay? So then this end up with x0, so which is true, okay? Then in general, then we have a dx x dot is both sides to ddt both sides, so you have this one and x0 and ddt of this one. But in this way, you need to ddt, be careful. You need to use what they call Leibniz rule. So in this side, your ddt, you have at phi tt0. So this is a property of transition matrix. But this one is not changed. So keep this one and study this one. Study this one, we are going to use Leibniz rule. Say for example, you have function here, function here. So you partial x in here and you integrate with sigma. So you end up with h partial g partial dg dx, and minus h, keep h unchanged, then df dx. Then plus, keep this at g and f, then do a partial inside. So that's Leibniz rule. Apply this one to here to see ddt here, partial t. So partial t, we are going to get the first one, g is t, right? G is t, f is a constant. So the partial f dx dt, this term should be 0, so this is 0. And this one is a partial t dt is 1, okay? So I copy this one, so it's 1 and 0, and plus, okay? Keep this one t0 to t unchanged, and then you copy it, you have partial this one, partial t. So then you have a phi, okay? A phi. You have partial phi, partial t, you have a t partial phi. So let me repeat. So we are talking about, we have x dot is at x So state transition matrix also satisfy T tau d dt is AT phi T tau. So exactly like this. So if we put together, we are going to see here is A phi x, okay, A phi x. And we have 1 in here, TT is 0, I is identity, okay? And then we end up with AT here, you have 5, 0, x 0, and this one. If you recognize, this is the solution of what? X of t, x of t. So we end up with x dot is ax bu, okay? So that's solution. Then if we add output equation here, things is also easy. So given this one, we're going to get y is c phi x 0 and c. So because we are integrated over sigma, so ct can bring from outside to inside. Then you have d and u. Okay. I know some of you may see this looks trivial because it looks so familiar in the linear time varying case. But here we can consider A, T, B, all those things are time varying. So you always have T comma T0, okay? T comma T0, T comma sigma, okay? T comma sigma. It's not a convolution, okay? It's not a convolution. Be careful, okay? Be careful. So today we are going to start from here regarding state transformation. So you have, this is my state variable x. How about I transform into the z? In many cases this is required to simplify the system. I will show you more soon. So the idea is p of t for any of the t, for all t, then p is differentiable and continuous and non-singular. Okay, so then we'll do d dt both sides. So remember I have two terms in here. Okay, so one is for the p, one is for the z. Okay, so then you just pull out dz, this term in here, and remove others. This one to this side. Remember, x dot is ax bu, here this is x dot. So then you have minus sign in here, okay? You move this one this side, okay? All right, so. But remember, x is a pz, right? X is a pz. So we can lump everything here. So you do p inverse both sides. On the left, multiply p inverse. And then you lumped this AP here, and p inverse. And minus p inverse, this p dot bracket. Here you have z. So this is like transform the AT, okay? Transform the AT. So it's not only just transformation of the AT, but also the p itself. Of course, when p is a constant, this term is 0, okay? Output equation, you can write the same. X is pz, so we can write the y is cp, z, and u. Initial condition should also be transformed like that. So the final solution, you can write it this way, okay? This way. So it looks, but it's actually simple. So this is state transition matrix for the z. So this is our case here. Output the equation will give you this one, cpz and du. So remember, x is pz, okay? X equals pz is my transformation, initial condition, the final solution. And so after the transformation, the state transition matrix and old original state transition matrix has a relationship with P inverse T. But remember, this is sigma, not T, okay? So be careful. So this is something we, after the transformation. Now it's ready to introduce a concept of two systems that are considered as equivalent or similar, okay? It's called similar. So two system is equivalent if and only if what? They have the same state dimension, the size dimension is the same. And for any of the every input, you have under the same input, there's an initial state, so the response of the system are the same. So take a picture of this one. So you have a system, you have a response, okay? System 1, you have A, B, C, D. Okay, so starting from T0, then we respond like that. But if you, so this is due to the initial condition, but if this is due to initial condition coming over here, and you have an input signal in here, so we have two parts of the solution. One is called zero state solution. So this is zero input solution. So this is kind of like zero input, this is zero state, meaning initial conditions are ignored, are all zero. So then you have another system, you also have something similar. So then of course you call these two systems equivalent. You also call similar zero state equivalence, meaning that you don't have so you don't have a initial condition. All the initial states are zero. Okay, all the initial states are zero, and then under the control, your output are the same. Of course, your initial states are different, although your inputs are the same, and the outputs will not be the same. And there's another one, it's called zero input equivalence. Initial states, the responses are the same for the zero input. So, meaning you have initial state are the same, then your response due to the initial states, they will be the same. So, zero input equivalence. So, and there's no requirement that state space be the same dimension. Okay. So in fact, if not the same dimension, it will be confusing. So I would like to say we are going to talk about same dimension. Same dimension. What I'm talking about is, so you have a x dot is ax plus bu, y is cx, okay? Cx. So if your input and output are the same dimension, but your internal states could be different. That's what this one is trying to say. So you have a single input, single output system. Your internal state could be different. So for the equivalence, in our definition here, we probably need all the states dimension are the same. So I don't want to confuse you too much. So just take a look. States are equivalent if you can find a non-singular state transformation P and connect these two systems. So then we call they are equivalent. Okay, that's why we need to study the transformation. Okay, so let's give you an example. Okay, so maybe you feel confused. So then let's say a second order system with omega constant. We know this is oscillator. Okay, oscillator. Okay. So then we can write ax plus bu cx, and this is a state space format. And choosing, you can put A is like this form, B like this form, C like. So in this case, you are going to corresponding to this one. Okay. So alternatively, you can do the following. So like using y as x1, y2, x dot, so then x1, x2 like that. So actually you can write A bar like this, B bar same, and C is 1, 0. So this one will also correspond to U and Y, input and output. So the internal states, X and that one is different. I want to understand how they are related. Are they equivalent? Answer is yes. If we assume I have a P that is omega 1, then I can connect P inverse A, P is the original one is like this, so this P inverse is here, and this is a P. So by doing this, we end up with this, okay? So that's why they are equivalent. They're equivalent. In other words, although I have a single input and a single output, like in this case, this is U, this is Y, so this is single input, single output, but internally I have states, okay? So I have expression of U plus, okay? I have U times B and plus, this is A, this is my X, but I need to integrate this is my X dot. So X dot is AX plus BU, okay, BU, okay? And Y is CX plus U, put it here, B, then you get Y. So Y is CX plus DU. So if I put the whole thing into a green box, so you have A, B, C, D, you have infinitely many A, B, C, Ds that can make this box the same as this. So from here to here is called realization. You put input output realized in such a way. So it's realization is called state space realization. State space realization. So among many of the realizations, okay, they are actually equivalent. In the sense that they are describing the same thing. So that internal representation using state space is never unique. Okay, it's never unique. Now how to make this unique, we are going to learn is called minimal realization. Minimal realization. But unfortunately, how many minimal realizations? Still infinitely many minimal realizations. How to make the minimization unique? So you need something called balanced minimal realization. To understand this, you need to understand what do we mean balanced on what sense. So then we need controllability and observability. So the equally observable and the equally controllable. So those concepts are kind of all connected together. Okay? So starting from here. So this equivalent kind of example to show you that we have a oscillation system from input and output, okay? So it's from a mass spring damper system. So this is nothing but you have mass, okay, on a frictionless surface, okay. So then you have a spring in here. So this is only first order system, right? But you have another spring in here. So you put a wall in here. So then you pull out in here, then you release. Okay? It will start to oscillate, and will not stop, right? So exactly by that. That's when U is 0, and then initial condition is not in the middle, okay? Then you release it, you will do this. You can also apply the U, okay, to force it to do a sinusoid. So it's oscillatory system. Okay? Even for that system, the state space expression is infinite possibilities. So, and there's equivalence in there. So of course, this is a linear time invariant system. And of course, this P of T is constant. And they are equivalent in such a way, okay? And of course, the P inverse B is 0, 1. Okay. Yes, what? So let's look at the time invariant system. So A and B and C and D are not time varying anymore. They are all constants. And we actually in the second class, we talked about why this is time invariant. To solve that one, we used some basic techniques like uniqueness, okay, uniqueness, and Grover-Feldman lemma, right? So by doing that, what's the difference is T minus tau. It's not T comma tau anymore. The state transition matrix is the exponential function matrix. So we're going to focus on that. But before we further discuss this one, we are going to review what is eigenvalue. Okay? Do you guys still remember what is eigenvalue? Eigenvalue for a linear operator. Eigenvalue for a linear operator, L. Think about L is a matrix, okay? So L is a matrix. And then it will be a scalar lambda times x. So for all x not 0, okay? If x is 0, it's trivially true, right? So lambda is in the vector is from the field, it's a scalar. So the x satisfying this equation is an eigenvector. The eigenvector of this operator. A matrix is operator, okay? Corresponding to this eigenvalue lambda. So shorthand is called E value, E vector, eigenvector. So I'm going to work an interesting example for you. So it can, eigenvector is never unique. Be careful because you can always scale this one. Okay, scale this one. Scale the x with alpha is always true for any alpha. So. But however, you may have multiple linearly independent E vectors, eigenvectors. Say for example, 1 is eigenvalue. But remember, the matrix 2 by 2 matrix is a unit matrix. So what is the eigenvalue for this one? You only have 1, but with multiplicity, what? 2, okay? It's a lambda square, so you have 2. So, but you only have 1 eigenvector. So x is 1, 0, which is true. Okay, you plot 1, 0 here. It's true. But if you get 0, 1, is also true. Okay, put it there. So, but these are all linearly independent. Okay. So this one and this one linearly independent. So that's why, although you have multiplicity here, that's nice. So then also you can normalize it in a way, like if we put this guy here, it's true. It's true. Okay? Okay. You put this one here, it's also true. So this is eigenvector, this is also eigenvector. So you can look very differently. Can you see that? So let's talk about matrix. A is n by n matrix right now. So those are, this is actually more general abstraction saying L is a linear operator. Matrix is just a special case. So linear operator from Cn to Cn, so you have n by n matrix. So then you have A minus lambda I is a identity matrix times x is 0. So what you need is a null space. X lives in the null space of this A minus lambda I. And so this is called null space of a linear operator. So non-trivial means x is non-zero. So null space we need to be, cannot be just 0, okay? And then that means the rank, okay, the rank of A minus lambda, okay, is less than n. Then if it is the n, this must be 0, okay? So you have a determinant of A minus lambda I equals 0. That means the rank is less than n. So then what we have is something called characteristic equation of this one, polynomial. So this is called characteristic polynomial. I'm not sure linear algebra you have learned this or not. Probably you have already. So fundamental theorem of algebra saying that have exactly n solutions, you should have n eigenvalues, and even you count those multipliers. So that's great. Okay? So there is something subtle for matrix. It's called diagonalizability. Diagonalizability. So you thought you have a matrix. You can do some similarity. You turn this one like lambda 1, lambda 2, and lambda n. So you can do a similarity transformation like n minus 1a n equals this lambda. Okay. We'll also talk about diagonal of lambda over 1 and lambda n. So we thought this is always possible, but I want to say this is generally is a wrong assumption. There are some matrices, fundamentally, you cannot diagonalize it. Okay? So that's why I'm going to show you next. So for example, you have a diagonal form, then you have all the eigenvalues that is distinctive. So then you have, there exist the n independent eigenvectors. So this Vn and the Vn, so these form a basis, and they are independent. So then you have V, A, Vi, and lambda I, and then you have V1, Vn until lambda 1, and you can stack together. You can write down like lambda n. So together, so finally you can write the lambda into this diagonal form, and it's also called diagonal lambda I, and V is like that. So it's AV is V lambda. So in other words, you can make this one. So it's possible. I said it's not always possible, but if yes, this is true, so how to find this m? Okay, how to find this m? So that we make this A matrix diagonal. How to find out this matrix? What is the way? You need eigenvectors. So let me give you an example. So you have a matrix like 3 by 3, and this is a diffusion rank 2, okay? It's a 0, 0, 0 in there. So the characteristic polynomial, we will see that det is like that. So you put lambda I minus that, equal determinant, you are going to have lambda times this, end up with lambda like that. So then you have polynomial like this. So your root one, lambda is 0 is one of them. So those eigenvalues are roots of the characteristic polynomials. In this case, lambda 1, lambda is 0, minus 1, and plus 2. So you have 3 of them. Okay? So the eigenvectors are non-zero vectors solves eigenvalue equations. So lambda I, so then I will try to find out the V so that making the A matrix diagonalized. So the first one is lambda I. So first is lambda is 0. Then second is minus 2 and 3. Okay. So given that, we are putting this one in. You have 0 times I. You have V is V1, V2, V3. So then we try to solve because rank A is 2. You have all 0 there. These are all 0, so rank is 2. So then we can put V1 as any number. You can put 1, you can put 2, okay? You could put any number here, arbitrary. Giving V1, you will be able to get V3 and V2. So it's end up with minus. So this V1 vector is not unique, okay? So you just get one of this. Then similarly, so you can also write V1 as this one, doesn't matter, okay? So you can put lambda 2 is minus 1, so you can repeat. Again, because of the rank is, this is a rank 2. Why? Because this column and this column are linearly dependent, okay? Dependent, the proportional. These two columns, okay? So arbitrary set V3 is 1. We solve V1 is 0, V2 is minus 2, so this is 1. So then we can do the same, and also we have the rank here problem. Okay, so this one and this one is a proportional. Okay, this one and this one. This column is proportional. So set V3 as 1 anything, and then you get the other 2 like that. So you have V1. So then you got V1, V2, V3, and add them together. So you are going to have a V matrix. Okay, V matrix. And you get a V inverse. This is a V inverse. Then you put V inverse A and B, you get lambda. This is exactly this lambda, diagonal. Lambda 1, lambda 2, lambda 3. So you diagonalize it. So that you have to use how to find out this V. Then you need to borrow those eigenvectors. And the scaling of eigenvector doesn't matter because then you need the inverse. Then you scale it. You scale this one alpha, then you get a 1 over alpha, inverse. So then you didn't do it. So don't worry about the scale. So that's distinctive. So 0, minus 1, and 2, they are distinctive eigenvectors. So what about I have repeated eigenvalues? So these are not distinct. Some of them are repeating. Okay. However, in this case, you still have a full set of eigenvectors. They are independent. So you still have n vectors that is independent. So they can form a basis. Same as case 1 is this case. If you have a full eigenvectors, okay, linearly independent full n vectors, they are not. Even is not distinctive. So these matrices, A class of matrix, they are called simple. Okay, simple. So for general, this is wrong. Okay, for general is wrong. But you see, for simple matrix A, then this is true. This is true. So this kind of thing is called simple matrix. simple matrix. So what is not simple? Okay. So we are going to see something not. So not simple for sure. The eigenvalues are not distinct. There are some repeating multiplicities there, and they don't have any linearly independent eigenvectors. So some of the eigenvectors are dependent. So then it's not a basis for the eigenvectors. Okay? So then the matrix cannot be diagonalized. Okay? So I'll give you an example. What's the difference between this and the unit 1, 1? This upper corner you have 1. Upper corner. So this kind of thing, although you still have eigenvalue, 1 and 1 and with multiplicity 2, but this matrix cannot be diagonalized. So this is called Jordan block. Okay? So then you check this one, you will see that you only have one eigenvector. You don't have a second independent one. So, because if you do this a minus lambda I, you end up with this thing. And this one has a rank 1. So this is called transformation to Jordan canonic form. I hope you start to see it. What is a Jordan canonic form? You have eigenvalues. You have n matrix, but you have p distinctive eigenvalues. So for each distinctive eigenvalues, and then corresponding to qi linearly independent eigenvectors, and put all the qi's together, okay, add together, is less than n, okay, total n, okay. So then each of the linearly independent eigenvectors for this is multiplicity here. So you have something like this. So you have a 1 all the way here. So this is called Jordan block. Jij. Okay, Jij. Okay, Jij. For each eigenvalues, Ji, you have each eigenvalue you have a block diagonal of the J like that, and so that's why you have Jij, and J is until 1 until Qi is independent. For each independent eigenvector corresponding to Jordan block. So maybe this is not very easy to understand, but in the end, you end up with this. You have block diagonal of Jordan blocks, and each of the Jordan blocks is another Jordan diagonal of Jordan blocks. Okay? So maybe this is confusing, but let's check on an example. Okay? So I think it's better to check on an example. And of course, adding all this thing together, you will have a dimension n. So P, remember, what is a P? P, you have a P distinctive eigenvalues. For each eigenvalues, you may have Qi's eigenvectors. Okay? They are linearly independent. For each eigenvectors corresponding to Mij's Jordan blocks. Okay? Jordan blocks. So let me go through an example. Okay? So this example is interesting, so you can play in the future. So you can see I have two eigenvalues in distinctive. Okay? The first one is 1 eigenvalues. The second one is 2. So this is 1 by 1. But for this 1, I identified this is a Jordan block. This is also a Jordan block. So you have 2 Jordan blocks. Okay? 2 Jordan. So I have 2 independent eigenvectors. But if I put this one is 1, okay? If this I is 1, then I only have 1 Jordan block, right? So So it's different, right? So in this case, I have a unique eigenvalues. P is 2. Two linearly for lambda is 1. The Q1 is 2. You have two linearly independent eigenvectors for lambda 1. You have two distinctive eigenvalues, 1 and 2. And you have one linearly independent eigenvector for lambda 2 is, so Q2 is 1. Okay. And N11 is 2. So this is N11 is 2. It's 2 by 2 matrix. N12 is 3. So, okay. And N2 is N21. It's the same. It's only 1 is 1. So this is 1. Make sense? Jordan blocks. It's confusing. Okay. But what is this one matters to our linear system theory here? So that's what I'm going to show you. So here is something called, if A is n by n matrix, then it's possible we can write A is similar to a unique Jordan canonical form. Okay? So except for a permutation of blocks, is unique in a sense. So go back. So you may say, if I bring this block and swap to this, put this one down, this one up, so it's still okay. Still okay. So that kind of permutation we should not count as not unique. Okay? So that's the reason. Okay? So it's except for permutation of blocks, we don't do the permutation. Okay? So in other words, so for general A, it is always possible to make it diagonalized, and we should say diagonalized with J1 until JP, okay? Until JP. So for each of this J1, you have another Jij diagonal. Okay, this is Ji. Okay. So there always exist similarity transform M to turn the A not the diagonalized, but you can do a diagonalized with Jordan blocks. Okay, Jordan blocks. So that's why we call it Jordan canonic form. So this is a Jordan plus canonic form. This one. This is a Jordan canonic form. Okay? J1 until Jp. P is the number of distinctive eigenvalues. Like our case, P is 2. In this case, P is 2. We have two distinctive. So J1 is that one. J2 is 2. Okay? So the whole thing here is called J1. Whole thing here is J1. Okay? This is J1. This is J2. Diagonal. Okay? So at this point, I hope you start to understand why this is interesting. The matrix eigenvalue, eigenvector, and Jordan canonic forms. This one is connected to what we're going to cover next time, called model analysis. So I'm going to go through those model analysis to put what we have learned here in practical use. So otherwise you will forget why we even learn this thing. Okay? So So here, we summarize about eigenvector, eigenvalue. We talk about A matrix could be simple. If A is n by n, if A is n by n and it has n linearly independent eigenvectors, then we call A is simple and A is diagonalizable. If it's diagonalizable, it's simple. But otherwise, in general, it should be transformed into Jordan form. So why we even learn that? The reason is, if you have an eigenvector, you can write something like that. It's a full set of eigenvector. Then you can diagonalize transformation by using eigenvectors to form this similarity transformation matrix P, so that the system can be similar. So in this case, P inverse A, P can be diagonalized with lambda I. Okay, this is a simple case, so we're talking about simple case. And by doing that, and then AP is P, this is diagonal, okay, P lambda, this is lambda. So then, for the zero, for the zero input response of the system, so you don't have a U, but you have as x0. How x will change according to that? This is nothing but time invariant case. Okay, so it's easy. But if we introduce, so in between A here, this is nothing but I, right? This is the identity. So it doesn't matter. I just insert this identity. I didn't do anything, right? But however, I can also add another identity here, P inverse. This is I, right? This is I. Okay. But by doing that, I pull out P inverse here, P in here, but I put this one here. Remember, I can do sigma Taylor series expansion. Then we can move the P inverse P to the exponential. To the exponential here, and this one is actually diagonal, okay, diagonal. So then, because it's diagonal, then the matrix is much easier to compute. So then we can make the output, the state response to the initial state like this. Remember, this is diagonal. So e to the power of diagonal times t is also diagonal. So then overall, this is a EAT. So that points you away to compute the matrix exponential. Okay. So if you do partition of P inverse like W1 and Wn, actually it stands for Hermitian, okay, complex conjugate. Okay. So don't worry about it. Just say a transpose. Okay, transpose. So this is n by n matrix, but you do a vector form. So this is called left eigenvectors. To make W left eigenvectors, you have W, A, and lambda W, okay? So then you can solve this W. So remember, we are ending up with, this is P, this is P inverse, this is exponential, okay, exponential. So remember, this is P, remember this is E, this is P minus, P inverse. So then in end, we just put this one to this, I get this, okay? And this one to x0 to this. So then we can write xt in a more compact form using eigenvectors. So with different this V is a vector, Wi is also a vector. So we write in this format, okay? So this e to the power of lambda t is called modes, okay, modes. Okay, you learn about vibration, you have vibration modes, different frequency and stuff like that. So what is essence of the system dynamics is, this is called modes. So this is also called mode decomposition. So then we can say others. So this is a projection of initial conditions on the left eigenvectors. It doesn't matter. And this one talks about the modes. So let's give you an example. So if you have initial condition, initial state here. So in this x1 and x2 is a state space. You have coordinates x1 and x2. So then you have eigenvector v1 is here, and you have v2 is another eigenvector like here. What do? You have one is longer, one is shorter. So this is called faster mode. This is a slower mode. So then you do alpha I is initial condition amount of present in the initial condition. So it's like you project this one parallel to here. You project another one parallel to here. Is alpha 2, alpha 1, alpha. So this is alpha. So then you are now working in the v1, v2 frame. Okay. Frame. Suppose lambda it is a decay or grow lambda. Okay, depending on the positive, grow, negative, decay. Then you have Vij, i's mode and j's component. Okay. Then your x0 will be able to evolve to the equilibrium point. This is called equilibrium point 0, 0 origin. So then this is initial condition going to here. So just like you have capacitor, the capacitor will discharge, then all the charge gone. So it's the equilibrium point, nothing left, right? So this is going from x0 to 0, okay? But how this red line is working, is going, that depends on the modes, okay? The modes and weights on top of the modes. So depending on where you start, you could start from here, you go this way, start from there, you go that way. So depending on initially where you are, you just decay like that. There is a fixed mode of. So then you should write something like this. So complex mode. So lambda. So if we have a complex conjugate, lambda and lambda bar, so you end up with this. So then lambda is sigma j omega. So then we will have something like this. This is a sinusoid. The magnitude is cosine sine. So then lambda bar is this. Lambda bar comes to this. Conjugate. So this will lead you to the real, and this one will give you something like this. So then x0 is here, phi m is here, phi is here. So if sigma is less than 0, rate of rotation of omega like this, so you are going to, m is going smaller, okay, because sigma less than 0. So this is smaller and smaller, so you become a spiral coming to, in the end, coming to the equilibrium point 0, 0. So that's, you can do a demo. So that's distinctive root case. On the other hand, if you have non-simple A matrix case, okay, then you need to talk about Jordan blocks, okay? So then you are going to have this, okay? Then you are going to have that. The J, you remember J, J1 and J and JP. So you get modes of the form like, do you see something different? You have this one and here. Okay, t to the power of kij and e lambda I. So this is your distinctive eigenvalues. But you also have this term. It's, it grows polynomially with t. Okay, but this is exponential. So I want to remind you that if you have t to the power of n, and e to the power of lambda t. And so say for example lambda is 0.00000 many 01, okay? And n is 1, 0, 0, 0, very, 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 very big, many, many zeros. Okay? So now the question is, when t goes to infinity, this one will be 0. Do you agree? Because you never can run as fast as you grow exponential. This one cannot grow faster than this guy. This decays faster, exponentially. So you need to look it out, you will see this is 0. No matter how small, no matter how big. Okay? So that's a good news. What we talked about eigenvalues, distinctive eigenvalues. Those eigenvalues really determines the fate of the decay or growth. And it is not the multiplicity of Jordan block stuff. So A matrix is not simple. It's okay. It's not going to change the fundamental things. So you are going to have like polynomials times exponentials. Okay? Polynomial times exponentials. So then still the exponential will dominate no matter what. Okay? So we're going to see an example next time, I think. It's a good idea we can stop here to see a Newtonian system as a